I hope you've had a good Monday. Letting people in, letting people in. Um, week 7. This is the last lecture for this course. Um, Once we're done with tonight, it's basically just finish up all the work and then take your HESI uh, Thursday the 28th and your comprehensive final on the 29th.
Recording in progress.
Not looking for anything special by saying this, but my birthday is on the 29th of August. I'll be 55 this year, and nothing would make me happier than to have every one of you pass your HESI and your comprehensive finals with flying colors. That would just be an amazing uh, birthday present. So you don't have to get me anything, but it'll do you some good if you did get me that. Okay. So let's go ahead and get started on tonight's lecture and see if we can make it happen, Captain. Any study recommendations for the HESI? Everything that you're already studying. There's not going to be anything new. There won't be anything that will be from out of nowhere or unexpected. And the HESI weighs the same as the registry does. They've uh, done their best to make sure that taking it on the computer, one, and two, weighing each section the way that the registry is weighed. So however many questions the spec says you'll have for safety, patient care, etc., that's what you're going to have uh, for the HESI as well. Okay. So it's it's essentially a practice registry is what it is. Okay. So there's no reason to be too anxious about it. I mean, obviously you want to know the material well enough to do well, but it's not something that's going to I'm trying to figure out a good way to put this. It's a good indicator for how you would do on a registry examination. Okay, so the materials that you're studying now, everything that we've gone over, everything in the presentations, all of that stuff is, of course, um, fair game on the HESI and the exit exam, as well as the registry. Thank you, Mr. Vera. But even though this is the last lecture and we still got week 7 to finish, and then week 8 you'll be taking your exams, I'm not going anywhere. I'll still be available uh, for a Zoom meeting if we need to have one of those, and by email or messenger. Okay, you guys. um, um, I'm not done with you until I turn in the grades. Okay. All right. So image production 2. There's not very many slides. However, there is a lot of information, and of course it does. I don't believe you have to sign up for the HESI. I believe simply enrolling in this course has got you set up for that. You just need to double check and find out what facility you'll be taking it at. So for this lecture, we're looking at equipment operation and quality assurance. So as far as the equipment goes, we make sure that we're familiar with the components that make up a radiographic unit, including the operating console, the X-ray tube, and of course our table, and especially our high voltage generator. Okay. So first, at our operating console, operating at low voltage, we have um, our controls for our technical factors there. We'll be able to select our tube current and the kilovoltage at the control panel, as well as turn it off, and any of the other devices that we may have at our disposal, be it fluoroscopy or automatic exposure control or anatomically programmed radiography techniquing. Our X-ray tube. Sometimes my mouse wants to work, sometimes it doesn't. As far as our X-ray tube, be familiar with the inner workings. Remember, it is enclosed in a Pyrex glass envelope. There are some that are made of metal, but primarily we're looking at a Pyrex glass envelope for our equipment. And the reason we use Pyrex glass is, of course, to withstand and be able to withstand the tremendous amount of heat that's going to be generated during X-ray production. On our cathode end, which is the negative end of the tube, we have the components for thermionic emission here and for focusing the electron stream across to the anode and our target. So we've got our filaments, large and small, our focusing cup. Then on the other side, the other electrode in this diode is, of course, the anode end, positively charged and biased, with a tungsten / rhenium anode disc, graphite, molybdenum, graphite and tungsten are going to make up the disc primarily. Now, graphite is used because we are having this large, heavy device that's going to spin at a very, very high rate of speed. Remember, for single phase through 3-phase generators, you're looking at about 3,400 RPM. For a high frequency generator, the anode spins at about 10,000 RPM. Now, because of those high rates of rotation, just like a wheel and tire assembly on your car, that needs to be balanced. And one of the things that they utilize for that is graphite when they produce those discs, because graphite is very malleable and you can take little bits of it out to help balance the disc so that it doesn't wear the bearings in the rotor end. Here, the stem, typically constructed of molybdenum, very, very lightweight, but extremely strong. Not that great of a heat conductor, but it does the job. Then, of course, we've got our rotor, which connects to the stem, and that has a magnetic bias to it and serves as the movement and moving portion of our induction motor, made up of the rotor and the stator. And if you recall, the stator is a group of electromagnets that form a ring around the glass and goes over that anode end. And so the anode sitting inside the glass, when we rotor up, that first stage of exposure, those electromagnets turn off and on and move the polarity around. And then, of course, the anode tries to match that polarity or is repelled by it until we get the rotational speed required for our production. Let's see here. I can see your message. And it's storming. Okay, just say that it's okay. It's okay. I understand. Yeah, if you get booted out, just make sure you've typed in before you get booted. If you get booted, you get booted. There's nothing we can do about that. Okay. Uh, and I am recording, so we're good as far as that goes. Golden, actually. So our electron source comes from the cathode. The heating of the filament, when we select our MA, we're going to select the amperage that's going to go through the filament, which causes it to heat up and boil off our electrons via the process of thermionic emission. Now, it's those electrons, when they move from cathode to anode, it's that movement of electrons that is designated in milliamperage. Okay, the current going through the filament itself is amperage in amps, and then the electrons in that stream of electrons is measured in milliamperage. Okay, that's important to remember that distinction. Focusing cup is primarily made of nickel. We'll hit some of the highlights here on this. Your target material, primarily tungsten, a little bit of rhenium, but the tungsten has a high atomic number, gives us a greater amount of higher energy X-ray when we energize the system. The induction motors driven by electromagnetics, and the two components are the stator and the rotor. X-ray tables, radiolucent. Be familiar with table movement and controls and how they're labeled. And then the high voltage generator we'll get into in just a little bit. Now, the high voltage generator itself is comprised of the filament transformer, the high voltage, high tension transformer, and the rectifier system. Those three systems all housed in the same metal box within the room comprise the high voltage generator. Other controls include the AEC, the automatic exposure control. Remember, the detectors are positioned between the image receptor, the grid, and the patient. So between the patient and the grid is where the detectors are. Make sure that we set a backup timer just in case there's a malfunction. We want to set about 1.5 times the predicted exposure. It's hard to predict what mass you would need for an individual based on their size measurement if you don't have good technique charts. So we're going to be kind of in the ballpark with these based on the technique charts that the digital system manufacturers give us. But remember, we want to be at that lower range of exposure whenever, just to stay within the confines of ALARA. Now, the other purpose of that backup timer, it does protect the patient, but it also protects our X-ray tube. Adjustments can be made on the master density control. The spacing between +1, +2, or -1, -2, or normal to -1 is roughly 25% of the exposure. Either an increase or decrease. The minimum response time. This is the amount of time that it takes for the signal from the detector to get to the machine and for it to react and say, okay, cut X-ray production. Remember that all of this is determined by electrons moving through conductors. And since electrons are physical pieces of matter, and the conductors are physical pieces of matter, there is an amount of time that it takes for the signal to travel from one area to another. It doesn't happen in an instance as it would with light. Okay. Electrons do not move at the speed of light through conductors. And so our newer machines have a minimum response time of about 0.002 seconds. And it's a 0.02 in older machines. Think three-phase generators as opposed to high frequency generators. Your manual exposure controls, also on the control panel. These are for our kV, our MA, and our seconds. Now, when we look at the circuit diagram, you may understand this a little bit better, but kV and MA are merely labels. Okay. When we adjust and manipulate the kV, we're manipulating what's going to go through the X-ray tube, but we're actually changing voltage in the circuit. When we adjust our MA, we're changing the amount of current that's flowing through the filament. And as I told you prior on the prior slide, that current is measured in amperes. The milliamperes is what's going to be flowing from cathode to anode in the X-ray tube, not what flows through the filament. We need a high current. KVP, of course, determines the quality, penetrability, and it affects the quantity of our X-ray beam. The more energy and kinetic energy those electrons have, the more likely it is to have for them to have multiple interactions at the target. The more interactions they have, the more X-rays we produce. Therefore, quantity goes up. MA merely dictates the quantity of X-rays in our X-ray beam. Seconds determines the quantity of the exposure over the period of time of that exposure. Okay, so it also determines how long those electrons are going to be flowing from cathode to anode, thereby producing X-rays. And remember, all of our technical factors are within our purview to control and manipulate as we see fit. Outside of the tube housing, we have our collimator housing. This will allow for manipulation of the light and radiation field. And remember, there should be a congruency between those two, meaning that the light field that we see on our image receptor and on our patient should be very, very close to the actual radiation field as well. Now, the only way that we can really get as close as we do is to put that collimator light the same distance from the mirror as our focal spot is from the mirror. If one of these distances is off, then the beam divergence will be off for one of those fields, and our light field radiation field congruency will be completely off. Okay. Now moving into our generator, which again has the transformers, both the filament transformer and the high voltage or high tension transformer, along with the rectification system. The purpose of the generator itself and our X-ray generator is to convert Um, Mechanical and electrical energy into electromagnetic energy. An electric generator very simply takes mechanical energy, converts it to electric energy. Okay. Transformers allow for us to adjust the voltage and current that's going to be flowing in the circuit. We typically describe them by what they do and based on what they do to voltage. So if the transformer that we utilize results in a higher voltage than what we started with, it's called a step up transformer. Okay. If the voltage is decreased, then it's a step down transformer. Now, um, the amperage and current is inversely changed based on the transformer and what it does with voltage. So in a step up, voltage goes up, which means current and amperage goes down, and vice versa. Now this is important to remember so that you can understand how we get kV and how we get milliamperage and why in the filament circuit we have amperage still as opposed to milliamperage, because I know that gets confusing for students. Now, the rectifiers themselves are diodes that are utilized to correct the current for use in the X-ray tube. An X-ray tube only operates with direct current because electrons in an X-ray tube can only flow from cathode to anode. Thermionic emission only occurs at the cathode. Since we can't heat an anode up to cause thermionic emission, X-rays don't flow, electrons don't flow back the other way. So to make the system more efficient, because we're using alternating current coming in off the wires into the building, into the generator, into the control panel, we have to at some point change that alternating current to direct current to be utilized by the X-ray tube. That's what the rectifiers are for. One note you do need to make here on this diagram is this line right here does not belong. So just pretend that it is not there. Okay. That is not a connection. So only follow the black lines here on the diagram. So first thing we come to on our diagram here is going to be first thing we need to look at is power coming in. Again, alternating current coming in here. Older systems have a line monitor that allows us to know how much voltage is coming into the system. Also, how much amperage is coming into the system. It used to be necessary because we would have to adjust because the electricity flowing through the grid and the city grid fluctuates from time to time. If the voltage is off just a little bit coming into the machine, it's going to affect the energy of the X-rays that reproduce. So we would have to check it after every exposure, before every exposure to see what exactly is the voltage coming into the system. If it was low or high, we could use a line compensator to manually adjust so that we get the correct amount of voltage in the system. Now the line compensation is automatic. There's it's all of our stuff is digital, and a lot of these things are controlled by computers or other types of circuitry, so we don't have to manipulate this anymore. That's why we don't see line meters very often. But those lines connect to the auto transformer, single coil. It does have a primary and secondary side. So the primary side would be all of these coils that we tap here from here to here. The secondary side is going to include the ones, all of these here, but we're only going to use a certain amount. So if we look at our filament circuit here, give me my pencil. looking at our filament circuit, which is all of this. Okay, it goes up to the filament, includes all of this down here. Now, on the secondary side of that auto transformer, we're only using this many coils compared to our primary side, which is all of these. All right, more coils on the primary side versus less coils on the secondary side means step down. So the voltage coming in, be it 110, 220, 440, whatever, when it comes through here, depending on the transformer ratio, the voltage is going to decrease. Okay. Now, when voltage decreases through a transformer, the opposite thing happens to current. Current goes up. So we've got amperage coming in 20, 40, 60, 150, 200 amps. Doesn't matter. What's going to occur here is our amperage is going to go up. Okay. And it's going to go up by the same amount that voltage decreased. Right? That's transformer law. So now we're in amperage, amps, in the filament circuit. We're going to get to our MA selector, which is a rheostat. That device is a variable resistor called a rheostat, and it allows us to change the amount of resistance that's going to be in the circuit. By changing the resistance, we change the amount of current that is allowed to flow through the filament. The more current we put through the filament, the hotter it gets, the more electrons we have. The lower the current, the lower the temperature, the less electrons we have. That's why we use the rheostat to adjust the MA, because ultimately it's going to change the temperature at the filament, which is going to change the amount of electrons that we have for our exposure. The next device after the rheostat is the focal spot selector. Which filament are we going to use, the large or the small? Okay, that's all that is. It's a switch. Pick one or the other. Now that is connected to the filament transformer, which has two different areas. We've got one for one focal spot and one for the other focal spot. But you can see on the primary side, there are more coils than on the secondary side. So more to less means voltage steps down, which means current goes up even more. So we're in a big amount of amperage on this secondary side. Again, high current, high temperature, lots of electrons boiling off via thermionic emission. Okay. Now, that takes care of the first part. Now, when we make our go to rotor up, that activates the filament circuit. So the current starts to flow, the filament starts to get hot, the rotor starts to spin because of the stator and that induction motor. The second part of the exposure, that pushing the button all the way down or pressing the other button, activates the timer. Okay. The timer is located in the tube circuit, which is all of this up here. Now, the reason the timer is in the tube circuit is because we want to control the production of X-rays, not thermionic emission. We want thermionic emission happening before and even maybe slightly after the exposure is done, just to make sure we get all the radiation we can out of the exposure. So the timing circuit is located in the tube circuit. It controls the X-ray tube being on, all right? The filament circuit takes care of the filament. Now, in our older devices, we had major and minor kV selections. Based on whichever we would pick, this would be 40, 50, 60, 70, 80, 90, 100, 110. All right? The closer that we get together, the lower our kV. Major kV jumps in this direction typically increase by 10 kV. Okay. Minor going in the opposite direction. This direction here, they're going to increase the kV by 1 kV. Okay. So if we go all the way to here, that's 110. And then we go 1, 2, 3, 4, or 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That gives us 120 kV for that exposure, depending on how they're marked. Now, newer generators, of course, we can go one at a time, 91, 92, 93, etc. But the principle is still the same. Again, we're operating with the auto transformer, so we've got all of these coils, and then however many coils we tap off here. Either way, we're typically going to end up with less coils on the secondary side. So voltage decreases slightly and amperage goes up. Okay? No big deal. We want to be operating volts. You want to make sure that the controls that we touch are in volts and not in kilovolts. So the control panel is always operating around volts and amperes. It's when we use this high tension transformer, a few coils on this side, primary side, lots of coils on the secondary side, we get a great increase, tens of thousands fold increase in voltage. That's where we get kilovoltage. Okay. Now, because our voltage is now in kilovoltage by going through that transformer, the opposite is going to happen to our current. So in this circuit, current goes from amperage down thousands of times to milliamperage. And again, milliamperage is going to be what is measured from cathode to anode in our X-ray tube. Okay? That's the current going that way in our X-ray tube. Now, we have to have alternating current in order for transformers to work. They do not work with DC or direct current. And the reason for that is if we have alternating current flowing through the conductor, because of electrodynamics, the movement of that electron is going to cause a movement of a magnetic field at 90 degrees. So it'll be completely surrounding this. Now, as the electron moves faster, the electron field or the magnetic field will open up. As the electron starts to slow down to get ready to go the other direction, then the magnetic field will collapse. As it starts to go the other direction, the magnetic field will open up again. So what we have happening in our transformer is that alternating current, because those electrons are going back and forth, back and forth, back and forth through the conductor, the magnetic field is opening and closing, opening and closing, opening and closing. Now, when it opens, it cuts through that secondary coil, causing all of those electrons to move. This is through the process of magnetic induction. Again, we're using a magnetic field to cause current to move and flow through a conductor. Now, since the magnetic field opens and closes a certain way, the electrons on the secondary side are going to move back and forth just like they were in the primary coil. All right. So still alternating current. Not good for our X-ray tube. So in this area, we have our rectification circuit made up of these diodes. Now, the diodes allow for electrons to flow in one direction and only in one direction. Based on our circuitry and our knowledge of current, electrons flow from an area of greater concentration to an area of lesser concentration via the path of least resistance. Okay, so good conductors and alternating current. So at some point in the electric cycle, in our older generators, we're talking 60 hertz. At some point, this side will be negative, this side will be positive, and we will be able to follow the electrons going through during half of that cycle. Okay, so from negative, we go this way, electrons flow into the arrowhead, follows this path, can't go that way, so it goes in, and we've got electron going through the tube. Once it comes out this other end, it could go that way, but that is back towards the negative area of high concentration. So it's going to actually turn back, go down this way towards the positive. Now, when these flip and this becomes positive and this becomes negative, we're going to use a different set of diodes. We'll be able to flow through here again from cathode to anode and then back out through this direction and back to the transformer. Now, again, this is all happening very, very quickly. 60 cycles per second, which is 60 half cycles, or it's 120 half cycles per second. And we'll talk more about that in just a little bit. So, does anybody have any questions about this portion right now? Was that too thorough? Was it not thorough enough? Anybody lost? Okay. Hopefully everybody feels that way, Ms. Sanchez. Lost in life. Oh, Miss Roque, that's of us. And that's a lot of us during x-ray school too. So, you know, you're in good company, trust me. Okay, so let's move to the next slide then. Speaking about pulses, the generator, phase, pulse, and frequency. All right, so real quick, phase just means how many lines of current are we going to have in a system, okay? If it's a single phase system, it's got one line of current that we'll be able to trace without any problem. When we get to a three-phase generator, instead of a singular up and down like we have here, positive to negative flow of voltage and current, okay? In this direction, on this side, one direction, on this side, the other direction. So this is what we're looking at as far as electrons moving through our circuit. Single phase, one line. When we get to three phase, arranging the electrical devices in a specific manner will allow for three lines of current and voltage to run in the same system. But because they're not, because they're configured in space just a little bit differently, they're offset. So they don't overlap. We don't have three lines sitting one right on top of the other. Okay. We've got three separate phases that are running at the same time that the machine's being energized. Now, single phase causes a problem. Without any rectification, again, X-ray tubes don't operate on AC. So if we were to take AC, non-rectified, and try to put it through a system, we're going to produce X-rays only half the time. Because on that negative half, X-rays can't, electrons can't go the other direction from anode to cathode. So half the time the machine's working. That's what we call half-wave rectification. If you put two rectifiers in a single-phase system, you can achieve half-wave rectification properly. Improper way is not to put any rectifiers at all and just let the X-ray tube do the work. by using 4 rectifiers, we take that negative phase, that negative swing here, and we flip it so that now the directionality of the current and the voltage is the same as it was on the positive side. So we fill in these gaps. And this is what is known as full wave rectification. The problem with full wave rectification and single phase is that the voltage dips all the way down to zero every 1/20th of a second. So we're only at peak for a very, very small fraction of that cycle. The rest of the time, we're either building up to peak or going back down to zero. This is why we have such a heterogeneous beam when we produce X-rays. This is what we know what's called as voltage ripple. All right. It goes from 0 to 100%, then back down to 0, and it's 100% ripple. That means if we set 100 kV, there's a very, very small percentage of X-rays that will be produced at 100 kV. The rest of them are going to be well below that, approaching 0. All right. So what we did was throw in some more electrical components, get 3 phases in there. Now, if single phase gives us 120 pulses per second, positive and negative, we flip that and now we've got full wave rectified, 120 pulses per second up there. If we just modify it and give us 3 phase, that's 3 lines. 3 times 120 is 360 pulses per second. Now, the good thing about that, as we saw with 3 phase here, as if we start with this solid line and trace it up, as it starts to fall, there is another potential. That second line is coming up and pushes the voltage back up to peak. As it's coming down, that third line is already coming up and it pushes us back up to peak. So we never drop to 0. Now, taking those 3 lines, three positives, 3 negatives per cycle, flip them up, and now you have doubled it. So we've got 6 pulses per 60th of a second. Now, that causes even less of a dip in our voltage. So if we look at 3-phase 6 pulse, it's measured out as 14%, which means that the kinetic energy that we give to our electrons flowing in our tube during the exposure only drops down 14% from peak. So at 100 kV setting, we're only going to drop down to 86 kV, whereas full wave single phase, we dropped all the way down back to 0. This means higher kinetic energies for all of our electrons, greater X-ray production, greater energies of X-rays being produced. Now, reconfigure electrical devices again, and we can double the amount of pulses from 6 to 12. This gives us a 4% voltage ripple. So at 100, now we're only dipping down to 96 keV with our voltage and our potential. That means more X-rays are going to be produced and they'll be at higher energies. By switching to a high frequency generator that uses a bunch of different devices and it flattens out the voltage ripple, and there's a bunch of things that go into this, we can achieve anywhere from, we go from 60 hertz to 500 up to about 2000 hertz, which causes our voltage ripple to become less than 1%. So from 100 kV max on our machine only down to just above 99 kV, which again translates to more X-rays being produced per exposure and higher energies of X-rays being produced, which is basically what this line sums up here. Less voltage ripple, greater quantity and quality. Now, changing the voltage ripple, making it so that we have less, maintaining that kV as high as it could possibly be to peak, has its disadvantages. Its biggest disadvantage is the amount of heat that it loads onto the anode and the target. That's what tube loading is referring to. This is the amount of heat that's going to be deposited during the exposure into the anode. Our maximum exposure time is going to be variable based on the manufacturer and its specifics. This is kind of like the backup time, but it's the maximum time that's going to be allowed. This serves as a safety net to protect the tube, specifically the anode, to keep it from cracking, melting, or pit, which is this in B. This is a high exposure, but the bearings in the rotor are also bad, causing the rotor to stutter. It doesn't spin smoothly. So consequently, there are areas in which the electrons striking the anode have actually caused the anode to melt. This causes a problem with tube output because it actually enhances the anode heel effect by absorbing more X-rays that are being produced down within these dips in the surface of the anode. So a lot of your systems are set up. So if you set a specific kV and you have a certain MA, there is a time it won't let you go past so that you don't get a specific mass to keep from overheating the anode. And so in those instances, if say you need more mass, you're either going to have to drop your MA so that we can get a longer exposure, uh, allowing for more time for heat to dissipate, or drop the kV so that you'll be able to achieve the amount of exposure that you're looking for. You do need to be able to calculate heat units and the heat capacity of an anode for the technical factors that you've set. And the way we do this is by calculating the heat units. And this is going to be in thousands of heat units, and you simply multiply the MA by the time, which is your mass. So multiply your mass times the kV that you're using. Okay. Then you have to know what type of generator you're using. On a single phase, this is simple. Just multiply the kV times the mass. Those are the thousands of heat units for that exposure on a single phase system. When we go to three phase and high frequency, the registry has combined those into a generator factor of 1.4. Technically, a three-phase 6-pulse generator is a 1.35, and a high-frequency generator is a 1.41 as far as generator factors go. But again, the registry has put those together, and we're using 1.4. So essentially what we're saying is that a high frequency generator, three phase or high frequency generator, will generate 40% more heat units per exposure than those same technical factors will on a single phase generator. Okay. There are some units that calculate that for you. And some of them go a step further and tell you how many times or how many more exposures with those technical factors you can load onto the tube before you need to let it rest and cool down. Okay, before we get into the components of fluoro, does anybody have anything? All good. Okay. So for fluoro units, um, again, we've got to have an X-ray tube. Um, and then we have to have a special type of image receptor. And most of the systems are going to digital flat panels or CCD type systems or CMOS systems. But point is, they're going away from the image intensified fluoro. Okay. The image intensified fluoro takes the x rays that are coming out of the patient, converts them multiple times so that we get a very, very bright image at the end of the image intensifier. Now, it is a fluorescent screen that is used in the image intensifiers. The special tables need to be able to go up to 90 degrees in at least one direction, up to 40 degrees Trendelenburg in the opposite if it doesn't go 90 degrees in the opposite direction. And another thing that I don't know if any of you have thought about it, but I know that a lot of places they like to do standing knees, standing feet, ankles, and whatnot. But fluoro tables and fluoro rooms are actually really good for that because you can put the uh, footboard on the end of the table and stand it up and raise the table up. Because sometimes those tubes just don't go down as far as you need them to when you're trying to use the wall board uh, or the wall stand. So, think about that. You can always use the fluoro uh, table for that. The fluoro tube is going to be underneath the table for most of your normal systems. Okay. That means the image receptor will be above the patient. There is a Bucky slot cover, so accordion style metal flap that'll fold when the Bucky's being pushed to one end of the table. They use much lower tube currents than X-ray tubes or regular radiographic tubes. Over the table imaging systems are going to result in higher radiation exposure to the personnel than tables that have the X-ray tube beneath them. So that's the reason why when you have a unit that is flipped and the X-ray tube is above, uh, a lot of those systems are remote operable. So there's either a control panel with a barrier that's movable that the tech can stand behind with the controls for the fluoro, or they just completely move out of the room and operate it remotely from behind the barrier. With our image intensifier, again, this is a diode. So with a diode, we have current that flows from cathode to anode. The image intensifier tube has a cathode, but the x-rays exit the patient and once they go through the glass, they strike the input phosphor, typically made of cesium iodide. Cesium iodide is prominent in radiography because it reacts so well to x-rays at producing light. Okay, so first thing we do, the input phosphor converts x-rays to light. Now, bonded to the input phosphor is the photocathode. Now, the photocathode is cesium antimony, and it is a metal that gives off electrons when stimulated by light. So the light photons that come off the cesium iodide hit the cesium antimony and electrons are released. Okay, so that's photo emission as opposed to thermionic emission. Light is going to cause those electrons to be released here instead of heat. So now we have an X-ray beam flowing through a vacuum tube. The electrostatic lenses surround that beam of electrons and allow it to keep its shape, tapering it down to a focal point, at which point it is inverted and flipped, and strikes the much, much smaller output phosphor. The output phosphor um, is on the other side of the anode. Now, the anode, instead of it being a large disk that the electrons strike, it's a metal disk with a positive bias that attracts the electrons, but because it's got a hole in it, it allows the electrons to pass through and they strike the output phosphor, getting converted to a very, very intense light. Now, when we turn on a fluoro system, there is going to be 25,000 volts or 25 kV while that system is on. That is going to be, that's the potential difference between the cathode end and the anode end. So those electrons are being moved across to that output phosphor by that potential difference. Okay, the only difference is we're going to produce light at the other end. We're not going to produce X-rays with those electrons. Now, the output phosphor is zinc cadmium sulfide. When Edison found zinc cadmium sulfide for use in the early fluoro systems, it was a very, very faint yellow green light that came off of it. The X-rays would hit, and then the screen would glow, and you would be able to see the anatomy. The problem was it's extremely hazardous because in order to see that, everything would have to be dark, and so you would have to be right there at the patient as the X-rays are coming out. So you're in the path of the primary beam as it's going through the patient. One of the fluoro systems at one of the facilities I worked at when I trained at when I went through X-ray school was a zinc cadmium sulfide screen in a tower without an image intensifier. So in that same metal housing, there was the screen. So the X-rays came out of the patient and the light would be given off, and it was in this dark tube that had a mirror at the top of it. That mirror would take the light and reflect it to another mirror outside of that tube. And then that mirror would reflect it down to another mirror that the radiologist would use to view the exam. So he's not standing in that direct path. Uh, that system didn't last very long, but that tells you how far. I mean, it's been 30 years. So going from zinc cadmium sulfide to the image intensified fluoroscopy was a huge step, because now not the radiologist is the only one that gets to look unless he points the mirror for you to see or gets out of the way. Image intensified allowed for us to attach a television camera tube to the output phosphor and generate an electronic signal that would go out to a TV monitor, so that now everybody in the room on the same side of the monitor could see the study, including the patient. Now, there are three formulas that you need to be familiar with when talking about the image intensifier. Okay, the first one listed. I want to pass it up. I want to go to the brightness gain. Okay, the brightness gain tells us about how well the image intensifier takes the X-ray information and converts it to visible light. Okay, we figure that out by multiplying the flux gain times the minification gain. All right, brightness gain is the product of flux and minification. Very simple. Now, the flux gain is the ratio of the number of light photons that come out of the output phosphor to the number of X-ray photons at the input phosphor. All right. Now, when setting that up, it's very easy to remember. With an image intensifier, you're going to have more light than you are going to have X-rays going in. It's intensifying it. Yes, I will. Okay, so since we're going to have more output light photons, that's the top number. The big number goes on top. with both of these both the gain formulas. All right, the both gain formulas, the big number goes on top of the divisor line. So output light photons divided by input X-ray photons will give us your flux gain. This is going to be a number greater than 1. Okay. The minification gain is the square of the diameter of the input phosphor. It's the ratio, the square of the diameter of the input phosphor to the square of the diameter of the output phosphor. Okay. The input phosphor is the big end close to the patient. The output phosphor is the small end where the light is going to come out. Therefore, the bigger number goes on top in this formula. All right. Now, the input phosphor diameter is variable. You can have a tri-field or a dual field image intensifier, which means you can have 2 input phosphor sizes or 3 input phosphor sizes. All right. So based on whichever one it is that you're using, you'll plug that into D1 on that formula. The output phosphor size is going to be either 2.5 centimeters or 5 centimeters in diameter. Okay. One or the other. It's never both and it's never interchangeable. If you start off with a unit and you know it's 2.5, it's always 2.5 unless they change it. Okay. The only variable phosphor in an image intensifier is the input phosphor, and it's always going to be bigger than 5. Okay. So again, a number greater than 1 for the minification gain. Now, once you solve flux gain and minification gain, take those two numbers, multiply them together, and that gives you the brightness gain. If you don't have an image intensifier tube, you may have a flat panel detector or a CCD type detector. They can be indirect capture, they can be direct capture. The most affordable is going to be the indirect capture, and that's why it's listed here. The indirect capture, if you'll recall, in our flat panels, takes X-rays, utilizes a scintillator to convert the X-rays to light, then the light stimulates the amorphous silicone in the flat panel. That gives off the electric signal. Okay. So that's what we have listed up here. Flat panel indirect capture or indirect conversion, either one works. We have to have the cesium iodide. Remember, that's also the image intensifier's input phosphor, cesium iodide. Again, reacts to X-rays by giving off light. That light goes into the TFT array. Now, the TFT array and the TFT are two different things. Okay. A TFT array contains a TFT, the detector element, and a storage capacitor. A TFT is a thin film transistor, which is an electric device that allows for the flow of electricity in a circuit. Think of it as a gate. All right. When the gate's closed, electricity is not allowed to flow. When the gate is opened, then the electricity is allowed to flow. The thin film transistor serves as an electric gate. All right. The charge during an exposure is not stored in the TFT, it is stored in the storage capacitor. But if the question says or asks if the charge is stored in the TFT array, then the answer is yes, because the TFT array is the TFT, the storage capacitor, and the detector. So you got to pay attention to the way the things are worded. The improvements over the image intensifier, they're smaller, lighter, they take up less real estate. The images are square, rectangular, as opposed to round. They have no distortion in them. We get a consistent image quality over the whole thing, as opposed to the image intensifier, which makes it a little bit brighter, and then it just kind of visionettes as we get towards the edges. That means it dims. Um, we get improved contrast resolution as well, because now that light is going directly into a specific address that is going to correspond to a specific pixel address in our image. Viewing systems, older fluoro equipment needed to use the television camera tube, which was the part that connected to the output phosphor, so that we could convert the light coming out of it to an electric signal that could be sent to a monitor or even to a VCR for recording purposes. Plumicon and Vidicon were the two primary types of television camera tubes. The Vidicon was the most prominent because Plumicon used lead oxide. The Vidicon used antimony trisulfide. I mean, anytime we can get rid of lead in an environment where heat has a tendency and a propensity to occur, that's a good thing, because lead heats up, it gives off toxic fumes. So Vidicon became the leader there, and they produced 5 cm and 2 cm output phosphors, or not output phosphors, but signal plates to be linked to the output phosphors. Of course, this would complete our television closed circuit TV system. Our newer digital systems, image intensifiers can be coupled to flat panel image receptors, but it's not a good thing, because again, the image intensifier's maximum output is 5 cms, but we could just use a smaller flat panel. But the preferred method would be to use a charged coupled device, a CCD or a CMOS type chip, because they are much, much smaller. Does eliminate lag. They are more durable. They're they're modular, so they're easily replaceable. Low cost as well. The recording systems for fluoro and our dynamic systems, we could use Cine film. The camera was positioned behind the output phosphor, and we would use lenses and mirrors to split the signal from the output phosphor between the television camera tube and the Cine camera, so it would be off to the side of the image intensifier tube. This did lead to more dose to our patients, but it was capable of recording at high speeds, similar to a movie, because it did so multiple small frame images that, it was actually like a film tape. The tubes had to be capable of handling the large heat load for all of the exposures that were made in such rapid succession. The other option was to couple the television camera tube, put an output on it to a VCR. So we could use VHS systems, high resolution cameras to record the studies. Our static methods included the spot film, which used cassettes. They were actually put into the tower and moved out of the way and held in a shroud, protected from radiation until they were needed. This is why there was a like 2 to 3 second delay, 1 to 2 seconds maybe on a fast system, because the film physically had to be moved into position in order for the images to be recorded. They would use 9x9s or some instances 14x14 cassettes that held film in them. The disadvantage here, again, the MA has to be raised to X-ray level as opposed to fluoro level, which is at about 2 to 3, maybe 5 MA. Now we got to go to hundreds of MA, so that takes a little time, again, to get that thermionic emission to occur and give us enough electrons. The other option was, again, using mirrors, lenses to split it, the signal from the television camera tube off to the 105 millimeter, which was roughly about this big. And you could take spot films like that. Uh, it was in a roll. And so when you were done with the fluoro study, you took the device off the tower, took it into the dark room, pulled the roll out, put a bend in it, took another larger piece of film and cut a slit in it, and put the roll and hooked it in there and ran it through the processor. So it would run through and develop. Once it came out, you would cut them all up and put them in little plastic protectors that would hold approximately, I'd say 12, 4 rows of 3. And you would put them in order, and that would go over into the radiologist's office to go up on the view box so he could look at those. But it could do approximately 12 frames per second, so it was pretty quick. Then, of course, we get to our digital fluoroscopy, which utilizes the charge coupled device or flat panels. And now we have the ability for post processing and electronic storage and distribution of those studies. Big advantages, big leaps in technology. Advantage for fluoroscopy included magnification, which we'll talk about in a second, but it did have a device that operated similarly to the automatic exposure control in static rad. The automatic brightness control or automatic exposure rate control was a device that could detect the amount of radiation coming through the patient into the system and adjust the KV, the MA, or both, depending on what kind of study it was, based on fluctuations in that exposure. Okay, so if we're doing a barium swallow on a patient, or even an upper GI, and we're following in an AP position, we follow the barium down, and then we have the patient oblique or turn lateral. When they do that, the part thickness changes. So the technique that's being utilized is not sufficient, and the ABC would increase the technique so that it would bring the brightness back to where it would be. Now, if you've done any fluoro, you would see this if the radiologist, sometimes the radiologist will stop fluoroing while the patient's making a move and getting into position. That cuts down on the adjustment itself, but when it comes back on, you may see it's going to be really, really dark, and then it'll get brighter very, very quickly. That's the ABC kicking in. Okay. Mag mode allows for magnification of the structures during the study. Now, this changes because the minification gain changes. Okay. I'm going to go back to that formula of minification gain so you can see what I'm talking about. Let's use simple numbers here for minification gain, okay? If we and we start off no magnification with an input phosphor size of 20 centimeters, okay? And our output phosphor size is 5, right? 20 divided by 5 is what? 4. 4 squared is 16, right? That is the minification gain for that system. Okay. Now, if we go to mag mode, when we do this, we're not going to use 20 centimeters. We're going to use a smaller area of exposure. All right. So let's just say we cut it to 10. Again, easy numbers. Okay. The output phosphor is still 5. So here we've got 10 divided by 5 is 2, squared is 4. Right? So by going into mag mode, using a smaller image intensifier, input phosphor size, we're going to decrease our minification gain. So in this system, let's just say that our flux gain here is 100. Again, I'm just pulling numbers out. Our flux gain is 100. Okay? For 20, input phosphor size of 20, our minification gain is 16. 16 times 100, well, that's 1600, right? So when we go into mag mode and switch to 10 for input phosphor size, 10 times 100 is 1,000. So by comparing these two, the brightness gain with 20 CMs is much more than the brightness gain at 10 CMs. So this tells us mathematically that when we go to mag mode and we decrease the input phosphor size, the resultant image is going to be dimmer. All right. Because remember, the flux gain is the number of output light photons to the number of input X ray. That's not going to change. We're not changing that. Right. So, in order to compensate for mag mode and that image being dimmer, we're going to get a change in technique. All right. Voltage will be increased. We're going to get better spatial resolution with mag mode. I mean, because you're wondering, well, if if all of these things are bad, patient dose goes up. Why use it? Well, the reasons why are better spatial resolution, better contrast resolution. We're taking these this size structure, and instead of displaying it in this field of view, we're taking that same size structure and using more of that field of view to represent the actual object itself. So mag mode, it very, very good, but it does increase patient dose. And now you know why mathematically. So the table, we've already talked about the table that needs to be able to move, right? Any questions on fluoro? To our digital imaging components. Okay. Ms. Ramos says no. So does Mrs. Sanchez. All right. So digital, very first system that we came up with, um, invented in the 70s. Kodak, first company to come up with CR, actually, which was kind of ironic because Kodak was huge in X-ray for film. But they came up with CR first. Fuji came out with the system clinically in 82. But Kodak started it, but Fuji came out with it clinically. Great systems too. Comprised of an image plate which is coated with a photostimulable phosphor. So we call it a photostimulable phosphor plate. Now, the phosphor itself is composed of barium fluorohalide. There are 3 halides which can be utilized for this phosphor layer. One is fluoride, one is iodide, and the other is bromide. Okay, so you've got barium fluorofluoride, barium fluoroiodide, and barium fluorobromide crystals that are utilized in CR. So we've got the protective layer, the photostimulable phosphor layer, the reflective layer, because when we make an exposure, a little bit of light, a little bit of that energy gets converted to light. The reflective layer kind of knocks it back into the phosphor for us. Then we have our base layer and then a backing layer, very, very thin sheet of lead across the back to prevent to help minimize backscatter recording. These systems require a plate reader. Now, the plate reader, in addition to pulling the energy out of the phosphor, pulling it into the computer, adjusting the signals, giving us our digital image, it is responsible for erasure of the plate, which is just a very, very intense white light that resets the phosphor, provided that we didn't give a lot of exposure to it the first time we used it. Thousands of exposures can be made on these image plates if you take care of them. Our DR image receptors, this one talks about the direct capture. Okay, we do have the indirect capture. It was described a few slides back in fluoro. Make sure you understand that we've got both of them in the digital imaging flat panels. Now, the difference between direct capture and indirect capture, where indirect capture, we're getting the image after we convert the X-rays to light. In a direct capture system, we're actually utilizing the X-rays that come out of the patient to generate our image. There is no conversion to light. Okay, that requires a different detector element. Indirect capture uses amorphous silicone. Direct capture uses amorphous selenium. Okay. Again, just like the indirect capture, we are going to use a thin film transistor array. There's still going to be a thin film transistor gate. There's still going to be the detector element, amorphous selenium as opposed to amorphous silicone. And there is a storage capacitor to hold the charge until the exposure is complete. So with the direct capture, no scintillation, light conversion is necessary or will occur. Very dose efficient. We get quick access to the image when comparing them to CR and film. There's, I mean, not even a split second difference between direct capture and indirect capture as far as image processing. Okay. We do get better spatial resolution. Before CR, or I mean, after CR and before the flat plates and the flat panels, after the television camera tube and before the flat panels in fluoro, we had the charge coupled device. This was the device that was utilized in all types of electronic equipment, from cameras to VCRs, in the public consumer goods. You know, your cameras, the first digital cameras and the first digital video cameras, aside from the digital tapes, were CCD devices because they were so small. They're very cost effective. Um, because of their small size, for an imaging system in radiography, we need an array of CCDs, which means we need multiple. In most cases, we would require 9 CCDs to make up and cover that 17 by 17 exposure area for these types of systems. So each CCD was responsible for taking the information from its quadrant. Oops, sorry. Didn't mean for that to happen. For taking its information from its little square here and putting it via fiber optic taper. That's what these little hairlines say. They take that large piece of real estate and minify it down to the CCD chip. Okay. Again, our advantages for these things, they respond to low scintillation levels. So as you can see in the diagram there, we do have a scintillator, the cesium iodide, converting X-rays to light, and then the light being tapered down by the fiber optics to the CCD. It's in the CCD, comprised of silicone, has TFTs in it, has storage capacitors in it. It's basically a mini flat panel. Okay. But it's a mini indirect capture flat panel. So it requires scintillation, conversion of X-rays to light, and then light to our electric signal. Because it is modular, any one of these goes out, it's easy to replace, very inexpensive compared to our flat panels themselves. The complementary metal oxide semiconductors, or CMOS systems, convert X-rays into light and stores them in capacitors. So they work along the same principles as the two separate components with the scintillator and uh, the CCD, but all of it is contained within this one device. It's got its own detector, its own amplifier. They're switched on and off, that allows for converting those electrons and light photons to electrical charges. Your non-scintillation systems, in other words, systems that don't require conversion of X-rays to light, have a high detective quantum efficiency than those that require the scintillator, which means they actually require less radiation to use. And the only exception to that is a few of the CMOS capture systems. Okay, components, stationary grids. We know we want our stationary grids. Most of them are focused, so they have to be within a certain SID in order to function properly and not have grid cutoff. The higher the grid ratio, the greater the scatter cleanup. The Bucky assembly is the device that oscillates the grid. The movement and oscillation of that grid is what prevents the grid lines from showing up during an exposure. Their movement causes them to be blurred, and then we can't pick them up. When you go do portables with a stationary grid, you will see grid lines. As long as they don't look wavy, it's okay. You don't need to repeat it because you're just going to end up with grid lines again. Okay. Um, for our DR systems, the Bucky assembly could include the detector, may not be removable. Compensating filters can be used to make sure that we attenuate a lot of the X-ray over thinner portions of the body. Right, the thicker the area of the compensating filter, the more absorption will occur in that area. So we get less exposure over this part of the T-spine. And with this trough, we get less exposure over the lung fields while still getting good exposure and penetration through the mediastinum and hilar regions. With our raw data and pre-processing, the information that's coming from our imaging system before or when it gets to the computer as an electric signal, it's got to be converted so the software can utilize it. That requires, excuse me, that requires the use of an analog to digital converter or an ADC. This is going to quantify the electric signal and give us distinct, discrete strings of digital data, ones and zeros. Okay. The length of that string is dependent on the bit depth of the software. Quantization reflects the accuracy with which each point is detected. Each pixel is assigned a numerical value and associated with specific shades of gray. Corrections are made via rescaling. This happens when the histogram is generated after the pixel count for the exposure, and the histogram is put into a lookup table. Those values are adjusted and we get our proper image. Corrections, another method of corrections is flat fielding. This is a software correction, and this can equalize the response of each pixel so that we get a uniform display. Really, if we look at this being an example of what we would see with the anode heel effect, where the anode would be at this end, and the cathode would have been at this end. Flat fielding would allow for an even tone across the image receptor. Dead pixel correction, the manufacturers try to maintain a standard of less than approximately 0.1% to 0.2% of defective pixels. And their software is utilized to identify and isolate those dead pixels. Once you get above that, then the software starts to be challenged a little bit. And so some of those pixels will start to appear in your images. Now, 0.1%, 0.2% may not sound like a lot, but on a typical flat panel that has about 9 million detector elements in it, 1% or 0.1% of that is 10,000 or 9,000. I'm sorry. Wait, million, 100,000, 90,000. Yeah, 9,000 pixels. 2% or 0.2 is 18,000 pixels. That's a lot of pixels. So with our histogram, the computer is going to analyze the data. Once it's gone through the analog to digital converter, it's going to do that and generate a graph, a pixel count, if you will, of different values. Okay. It's going to determine, based on the algorithms that are already inside the system, what parts are outside what we refer to as the values of interest. And the values of interest are those values from low to high, which should correspond to specific anatomy. Okay. Once it identifies the values of interest, it can make an adjustment based on the lookup table. With CR, doing 2-on-1 was not something that a lot of people attempted to do. And I think this was one of the reasons why techniquing kind of took a downward turn. We would do this with film. And unlike CR, where if one of them's dark and the other one's light, you just go over to the other one and window it a little bit and it'll look good. And then you just go back and window the other one. Every one of those images had to be the right density and contrast. So we had to be very, very careful with the techniques that we set, going from a PA wrist to an oblique wrist to a lateral wrist. So they all appeared the same density wise and contrast wise. That required being very good at adjusting techniques. You don't have to do that now. You can use the same technique for CR and they'll be close. And if they're not, you can just window it. If you weren't close with film, you had to repeat it. But CR did have this quirk where if it didn't recognize four collimated borders around an area of high concentration of data, it would assume that all of the information was part of the image and consequently was part of the anatomy. And so when the lookup table would go to make an adjustment, it would lengthen the histogram. So the values of interest and the number of them grew. And so we would get what was known as a histogram analysis or a rescaling error. This is where the image just looks dark. With film, we wouldn't have been able to see this scatter. It wouldn't have shown up. That's how low of an amount of radiation it is. But CR, extremely sensitive to low levels of radiation, just like our flat panels are. And so consequently, what would never show up on film actually showed up in these rescaled images. Now, these don't have to be repeated. With film, they would be, but with CR, you could basically just go in and tell it, this is the area that I'm interested in, and it would automatically rescale it, and that would fix both exposures. Your grayscale is the number of shades of gray that can be stored and displayed in the computer system. Post-processing technique that is useful for highlighting small high contrast structures is edge enhancement. The problem with edge enhancement is while it is good for small structures, it doesn't really do anything for the overall appearance of your image. Okay. This is where our image noise could be increased with a post-processing technique. Equalization is a process that alters the pixel values across the image so that we get a more uniform appearance. Smoothing or low pass filtering is utilized to reduce image noise and contrast. Again, useful for viewing small structures such as fine bone tissue. And what it does is very similar to noise reduction, is it takes an area of high contrast and then takes the values of the pixels around it and averages it to go in the middle there. And so with an unfiltered, we got this, we throw on the edge enhanced and it starts to look pretty good. But smoothing gives us that unfiltered appearance, again, because it's averaging neighboring pixels to determine the values that are going to go there. So spatial resolution does get degraded with a smooth. These are extreme. By no means are we saying that these are diagnostic examples here. It's just to give you a very, very, very good visual kind of, this is what it looks like kind of thing. Now, the values of interest, again, are what's going to be adjusted by the lookup table. The lookup table has a contrast curve assigned to it based on the anatomy. These are all pre-programmed. In Fuji systems, we actually have access to these and can manipulate them. Konica, not so much. But that's why I love the Fuji system. But anyway, what happens with the lookup table is the values of interest go in to the system, are put up against the lookup table, which says, okay, if it's 40, it needs to be 90. If it's 30, it needs to be 10. So it increases the contrast of the resultant image. If you have worked with CR, and even if you've worked with DR, most of the time when you make an exposure, there's an image that comes up, right? Real ugly, gray. You're like, oh my gosh, it's underexposed, especially when you first started working with these types of systems. It's like, oh, that's terrible. But then it would disappear, and you're like, where'd it go? And then it would come back and it would look beautiful. That was the lookup table being put on the original, the raw data. The very first image that comes up is the grayscale, high gray, low contrast, sometimes grainy looking image. That is pre uh, processing. That's the raw data. Then the image that comes up is after the lookup table has been applied and all of the values have been adjusted on that image. Post-processing adjustments, brightness. Brightness is adjusted using the window level. Increasing the window level increases image brightness. Because we're so well versed in the inverse square law and know that the closer to the source of light or energy, the greater the intensity. Okay, so I think of a window being on a wall, right? A real large wall. The higher I take it, the closer it gets to the sun, the more light that comes into the room. The further I get it down the wall, the further away from the sun it is, the lower the intensity of light, the darker it becomes. Window level, all right? Window width is going to adjust the contrast. We have a certain number of shades of gray from black to white. That will fit through a window of a specific size. If the window is only this big, we're not going to be able to fit in a scale this long. So we adjust our scale so that it fits the window. And actually, what we do is we adjust the width of the window to fit the scale. So window width changes the number of shades of gray, increases contrast, decreases contrast. By widening the window, we allow more shades of gray. Post-processing again with the region of interest. Say you have a lumbar spine, okay, and it's just not looking great. You don't like the way that the lookup table gave the contrast and put it up there for you. Maybe the patient was large, okay, so we've got a lot of grays in there. You can adjust the region of interest post-processing just around a specific area of tissue, and it will apply those values to the rest. It'll process the image over and it will change the scale of contrast. Electronic cropping or masking. We want to use this we utilize this to get rid of the bright edges on the collimated edges. The rule, the general practice is if it gets x-rayed and is irradiated, their remnant radiation must be captured by a receptor, and that image must be read by a radiologist. It must be interpreted. Okay. If we expose it, it needs to be interpreted. We do not need to be going in and collimating or cropping and masking off anatomy. There already have been too many lawsuits from have been a result of diagnosis or misdiagnosis or an error in diagnosis because we cropped off something post processing. Stitching, can't fit it all on one, but you need it all on one. CR is the way to go, where we're able to take multiple images and the computer is able to take the values from those images compare them very, very quickly and then generate one continuous image of that anatomy. We have 11 slides. If you need to go ahead and bolt. If not, I'm going to continue. The last slides will go very, very quickly because it's mostly just percentages of error and times, as well as tests. So it's very easy for you to review. Two types of monitors that can be used. Cathode ray tubes, not very common anymore. They're too big. They really are. They do have good resolution, but there is some distortion that goes in with those. Plus, they give off low levels of radiation. Liquid crystal displays, they're flat. The dimensions are thinner. They take up less real estate on a desk. Viewing conditions, low level of ambient lighting. Most radiologist reading rooms are going to be extremely dark. I prefer that in my control area as well. If I'm QCing x-rays, I don't want a lot of ambient light. I want to see the image. I don't want to have any distractions from the image by any other lights. So we want to position the monitors away from direct light sources and reduce any reflections. Note that because LCDs are primarily made of plastics and polymers of that sort, CRTs require glass. So their faces are always glass and they do reflect light more than an LCD would. The spatial resolution of the monitors. Here's some details here. The matrix of the monitor should be at least as large as the image matrix. Now, that rule does not necessarily apply to our workstation monitors. The workstation monitors are typically the poorest of all, okay? Image quality will decrease, but again, we're just diagnosing the image. We're not making a diagnosis of the anatomy. So that image quality doesn't have to be on par as it is for the radiologist. High resolution 5 megapixel monitors are recommended for reading, possibly even in physicians' workstations as well. For brightness, the primary display monitors should express a luminance between 500 or 3 to 500 candela per square meter. The ratio of maximum to minimum luminescence is recommended to be at least 250 to 100. Okay. 14-bit digital imaging systems are capable of producing 16,384 shades of gray. And so this requires a monitor that will be able to display that many shades of gray, at least that many shades of gray. Additional concerns include geometric distortions, whether the front is convex or concave, as far as the curve of the screen. Veil glare, which is the white area. The veil glare, the veil glare itself is a chemical reaction in the eye to the white border around a radiographic image. So something really, really dark, and then you've got that very stark white border that causes a chemical reaction known as veil glare. And so that's the reason why the masking is there to begin with. And it's really for the radiologists so that they don't have problems when trying to make their interpretations. Display noise. Image noise is not always in the image. It can be electronic in nature and it can be generated by the monitor itself. For informatics, the DICOM, Digital Imaging and Communications in Medicine, is a protocol required for all image acquisition. Okay? CT, CR, DR, fluoro, MR, ultrasound, all of the modalities, in order for those digital images to go into PACS, there has to be a DICOM to communicate with those systems and PACS. Okay? Every manufacturer's got their own. We can't just use one for all of them. So DICOM is the communication standard for information. Thank you very much. Uh, for digital imaging. Okay. Um, PACS, of course, is the picture archiving and communication system responsible for receiving, storing, distributing, displaying digital images. Communication between the RIS and the HIS, the radiology information system and the hospital information system, is accomplished with the HL7 protocol. This is health level 7 protocol is needed for the HIS and the RIS to communicate. Because remember, the hospital's information system is not the same as the radiology information system. The EMR or the EHR is the electronic medical record or electronic health record stored in the HIS. We merely pull little bits of information from the EMR into the RIS for radiology. Now, there is a little blog here and a link. Answers the question, what are the differences between PACS, RIS, CIS, and the DICOM? Goes a little bit more in depth. Some students have found that to be very, very useful. Let's see, exposure indicators. We've talked a little bit about those. Remember that there are different ones. They vary by manufacturer. S number, EI number, the DI, the exposure index, all describe a little bit about how much exposure was put to the patient and how much computer processing was done to the image. Okay. The closer you get to whatever uh, ranges parameters they have set forth for you, that gives you an idea of where you are as far as exposure goes. Okay. With the S number and CR, the perfect exposure to an image plate would yield a 200 S number. That was equivalent to 1 milliröntgen of exposure to the plate. Now, some uh, procedures may require a 400 S value. Well, from 100 to 200, that is a halving. Or so from 200, sorry, we start at 200 is perfect. 200 to 400 is a twofold step, which means that the exposure is cut in half to yield 400. Cut it in half again, you yield an 800 S value. Go the opposite way. From a 200 to a 100, you've gone to 2 milliröntgens. You've doubled the exposure. From 100 to 50, you've quadrupled the exposure. So they're guidelines to help you with exposure, because with film, if it's underexposed, it doesn't look good. If it's overexposed, extremely overexposed, it doesn't look good. And you had all sorts in between, optimal and overexposed. But when we get to digital, aside from the noise at underexposed and the saturation where we lose contrast at the extremely overexposed, you really can't tell the difference between overexposed and optimal. And this is where dose creep comes into play. So the EI and the exposure index is there to it's there to guide you as a technologist in your techniquing for future exams. Quantum noise, known as quantum model, uh, typically a result of incorrect exposure, a decrease in the amount that's required. Again, magnify your image on your workstation to see if it disappears. If it doesn't disappear, it is part of the image. It needs to be repeated in most cases. Um, if you're not sure if it needs to be repeated, ask the radiologist. Ultimately, he's the one that's got to read it and decide whether or not that noise is acceptable. If it disappears, then the exposure was right and the noise is a result of something else, either electronic or monitor wise. Gross exposure errors cause a loss of contrast, like we saw with that hand previously. Um, Saturation results in an overexposure, is a result of an overexposure where the machine the system just cannot handle it and it results in burnout. It's at this level we run the risk of actually uh, burning out pathology that would otherwise be visible with a lesser exposure. Evaluate your images for contrast. Um, you know, could you collimate more? Really, you want to be looking at your index, see where you are there, because like I tell my students in my program, the contrast is controlled by the computer. Subject contrast is based on our technique, but our image contrast, that's up to the computer and the algorithms that they've already programmed in there. Remember, your spatial resolution is measured in line pairs per millimeter. Do you have good spatial resolution? Did we using the correct SID? Did we minimize our OID and eliminate all motion? Okay. Did we get a good representation of the part that's imaged by minimizing our shape and size distortion? Two-part film alignment on? Do we have any foreshortening? Any elongation? Did we mark correctly? The mark side, if we're doing a left, did we mark the left and mark it with a left marker? Look for artifacts, grid lines, or the moire. This is the grid line artifact that we worry about. They're very, very big bands and it's wavy. Stationary grid with a portable is very, very small, very tiny grid lines. That one we're not going to get rid of. Okay. Uh, Scratches or damage on the IR, light spots, banding, fluctuation in the speed as the image receptor is moving through the reader. So these are CR type things that can occur. Ghosting or phantom images as a result of incomplete erasure. Heat can cause fog. Heat can also cause blur. It's important with CR, get those processed within an hour of exposure. Um, that's excessive to be waiting that long to process an image anyway, but after an hour, the image will start to degrade. Radiation fog, another thing you want to look out for, that decrease in contrast over the whole image. Okay, these last 4 slides are quality control. Okay, the light field, radiation field alignment needs to be within 2% of the SID. You can use a special cassette for this, or you can go the cheap route and do the 9-penny test. Okay, you can use an 8-penny test. The point of the 9th penny, though, is to mark either cathode or anode, so you know what collimator is off. Okay, now the reason we use pennies, the reason we don't use dimes, nickels, or quarters, is because of that margin of error. Okay, 2% of the SID, plus or minus. The diameter of a penny radiographed sitting on the receptor at a 40-inch SID is exactly 2% of 40 inches SID. So when we put those pairs of pennies on in the middle of the long collimator areas, if any of the right, so we're gonna turn the light on and we'll put our pennies down. Okay, then we'll make the exposure. Right, the light field is represented by where the pennies connect. Here it's dead on. The radiation field, if it's congruent, should fall right between the two pennies. Here it's a little off. Here it's a little off more than it is here. And here is about the same as here. So this one is the only collimator uh, leaf that is dead on with the radiation field and the light field. Now, are these within that 2%? Yes. If the radiation field extended beyond the diameter of either one of these pennies, then we're outside of the 2% margin of error. And we would have to call someone in and they would have to make an adjustment to that unit. That's why we use pennies. Should be done quarterly, should also be done upon installation. In fact, all of the tests that are named here need to be done when the unit is put in and at their prescribed intervals. Central ray alignment there's a special device that goes on the cassette that you mark your center hashtag, place that on there and make the exposure, and it will show you how far off you are. There is a 1% variance allowed in that. Recognition and reporting of malfunctions of our equipment is the responsibility of the radiographer. If you don't know how it works, if you don't know how it's supposed to operate and how to operate it, you cannot be an effective technologist in this aspect. And remember, knowing the equipment, knowing when it's working right, and knowing when it's not working correctly is important in radiation protection as well. Anytime you identify a malfunction, report it to the shift supervisor or the DOR. Get somebody on it, let it get fixed. Detector calibration. Depends on the manufacturer and what they prescribe. Can be daily, can be weekly. This is just to make sure that the detector itself is operating properly, including doing a flat field and dark noise tests. For CR, we want to have a plate reader calibration. QC tests for erasure on CR should be done weekly. Cassettes should be done on, they should be cleaned on a regular basis as well. Check daily visually, have routine cleanings. For spatial resolution, focal spot size, you're allowed a 50% variance, okay? The pinhole camera, slit camera, and the star test pattern are the tests for spatial resolution. The easiest, most popular one to do is the star test pattern. This should be done yearly. Timer accuracy would utilize an electronic synchronous spin top. For settings greater than 1/100th of a second, there's a 5% plus or minus variance in the timer setting. For times less than 1/100th of a second, there's a 20% margin of error for variance. Okay. KVP needs to be plus or minus 5% or plus or minus 4 kV in its margin of error. And there's a special cassette that is utilized for the KVP QC test. That's called the Wisconsin test cassette. Remember that half value layer is an indicator of beam quality. For a new system, anything operating at over 70 kV or with the potential to be operated at over 70 kV needs to have at least 2.5 millimeters of aluminum equivalent. Mass can be checked for linearity, reproducibility, and reciprocity. Okay. Linearity, consistent radiation for different combinations of MA and time, where we have no more than 10% variance. Okay, so if we set an MA and set a time and then make an exposure and then double the time or double the MA or half the MA, that should be consistent with a decrease by a factor of 2 in exposure. That's what linearity checks. Reproducibility checks for the same radiation output for the same mass setting. Set 25 mass, we need to get the same output for consistently through there within a 5% variance. Reciprocity is if we want 25 mass, but we're going to use 500 MA at a certain time, and then we're going to go back and use 100 MA at another time that gives us the same MA. Okay, that output can be off by no more than 10% in the reciprocity test. Fluoroscopic exposure rates need to be done every 6 months. Lastly, get out of there. Display quality assurance, the grayscale standard display function should not vary by more than 10%. Luminance is on a previous slide. Recommended luminance for a primary display monitor should be between 300 and 500 candela per meter squared. The ratio of minimum to maximum luminescence should be at least 250 to 100. And then for our accessories, our shielding, lead apron, and glove inspections should be performed annually. In spite of my affinity for Bouchon, in his book, it does say that you should you should fluoro your lead aprons and your gloves. You should not fluoro any of your lead protective equipment. The ABC is designed to look for a specific amount of radiation. These pieces of lead apparel are designed to absorb X-rays. So what happens when you put lead in front of a fluoro? It's going to run and increase the technique until it penetrates that lead. That causes wear on the tube. You shorten the lifespan when you go through 50 to 100 lead aprons to fluoro them. The NCRP recommends a visual inspection annually. Okay, visually lay it out flat. Look at the cover. Check for the frays. If it is frayed, see if it affects the lead or the integrity of the lead impregnated vinyl. Then have it laid out flat. You're going to use your hands and tactily inspect. Rub all of the areas of the lead, feeling for creases, divots, possible holes. If you do not locate any, the apron is good to go. If you do find something, you're to take an image receptor and make a single exposure of that area, inspect the radiograph for the hole or the crack, whatever it is that's suspected. That is how the annual inspection should go. Fluoro, and I know everybody does it. It's the same thing here. I teach this stuff, and they do fluoro anyway. But I'm not having to pay for their tubes whenever they go out, so it really doesn't matter to me. But the big thing here, the big takeaway is annually these protective devices need to be inspected. Okay. Any questions about anything that we talked about today or tonight? I tried not to go too long, but I definitely wanted to be thorough. This is an area that I really enjoy anyway, so it wasn't a problem for me. I hope you enjoyed it. I hope it opened some doors in your mind about the equipment. And as this being our last lecture, I will still post you some announcements on Friday and Monday of next week. All the best of luck to you. Study hard. Try not to overdo it. There is such a thing as studying too long. So, if you're used to going 4, 5, 6 hours and you're not doing well, cut that time back. Just go a couple hours, go 1 hour, go 30 minutes, take a break, come back to it. Okay. you can get overtired. Thank you. Thank you very much. Remember, I'm still here. If you need me, reach out. I'm happy to help. Good luck with everything. Thank you very much. Thank you, guys. Good luck. I'm pulling for you. I'm pulling for you.
Record